Hello everybody, here is your bell ringer question. This can be found in Google Classroom. I would like you to look up the information on this. So please pause the video and go answer this question in Google Classroom. Alright, so what is a capacitor? What are the units of measurements for a capacitor, and what is a capacitor used for? So if you just Googled capacitor, you probably found something that was cylindrical in shape, like so, with a couple of wires kind of hanging off the bottom. Okay, these are kind of what capacitors look like. You might have saw something like that on it, but a capacitor is an electronic component that essentially works as a temporary battery. Okay, and their units are farads. So a lot of the times it's like microfarads or nanofarads, but it should be labeled on the side of them. Okay, and like I said, a capacitor is used for a temporary battery. Sometimes if you turn off, let's say you might have a charger, a cell phone charger or something like that, and there might be a little LED inside of that. Okay, that light will stay on temporarily when it's unplugged. That's because there is a capacitor inside of there that's storing power. It's trying to keep a memory for the object, or keep a memory for the electronic components. Okay, so it's essentially like a temporary battery. They're kind of cool. They're also used for short bursts. So like a camera flash would use a capacitor, because they can have all the energy stored in the capacitor. Okay, and then as soon as somebody pushes the button on the camera, right, let's say our flash is up there, as soon as somebody pushes the button on the camera that connects the circuit, the flash goes off. It kind of gets released all the electrons, all the power into that flash, and then as soon as that battery is spent, then your flash turns off. So depending on the LED in the flash, you'll have a specific capacitor to match that. Okay, so today we're looking at a little bit more with circuitry. We're going to look at components, and we're going to actually get out the Mr. Circuit Labs, and we're going to be able to do inventory by the time we're done. We won't put anything together today, but you'll be spending more time on solving circuits. Okay, so starting off, that's what we're going to start with for review. Okay, so voltage, what is a volt? Okay, we talked about this before. Maybe we didn't necessarily give it a specific definition, but when 1 joule of work is required to move 1 coulomb of charge, okay, so you remember that word. So that's the measurement of charge for electrons from A to B. So 1 joule of work moving 1 coulomb of electrons from A to B, there's a voltage of 1 volt. Okay. Voltage is measured with capital V, or like italicized V. Okay, it requires both the magnitude and polarity. So we have to have a specific amount of voltage, and it's got to be positive or negative. Okay, a lot of the time when we measure things, they're measured in positive charges. When we end up getting something like this where you have a negative charge, that means your setup might be backwards. Okay, so you might switch around the leads, and it'll go from a negative 5 volts to a positive 5 volts. Okay, so the next topic is wire gauge and resistivity. So we've discussed this a little bit before, but the resistance of the wire is determined by the resistivity of the conductor, and it also depends on the geometry. Okay, so what this means is like the chemical makeup of it. Is it gold or silver, or what we use gold quite a bit. Okay, gold is probably one of the best conductors. So if you see more expensive electronics, then it's going to have gold parts to it. And then what we mean by geometry is the cross-sectional area. So that would be how thick is the wire, or how thin is the wire. Okay. So if you have a really thin wire, it's going to be a lot more resistive than a larger wire. Just think about trying to put water coming from a fire truck through a garden hose. It's not going to work very well if we're trying to push a lot of water through there. It's just going to be subject to the size of the garden hose. Okay, so resistivity is equal to rho times the length over the area. Okay, and we're not necessarily going to be using that, but just an equation for you to see. Okay, but in most cases, wires are going to be assumed to be 0 ohms, just for the sake of calculating the voltage in the circuit, which is what we're going to do right now. So a little bit of review here, practice. Calculating voltages in circuits. Okay, so you're going to want a piece of paper for this one. If you don't have one out already, most of you probably do. But we're going to practice solving this circuit. So we have this resistor, and this resistor. Now I have it a little bit different now, where there's two separate charge pumps or batteries. Okay, so these are in series. That means they're right connected to each other, so we can add their voltages together to get a total of 6 volts. Okay, so over here in our table, we're going to have our 3 ohm resistor and our 6 ohm resistor and our 2 ohm resistor. So this will be resistor 1, resistor 2, resistor 3. This looks a little bit different from the positive physics stuff because this is a worksheet that you guys are going to have to work on this stuff. Okay, so remember, for total resistance in a series circuit, we're going to have resistor 1 plus resistor 2 plus resistor 3. Okay, the voltages in a series circuit will be the same. Voltage 1 plus voltage 2 plus voltage 3. Okay, those all just add together. But the amps, okay, the amperage, your total amperage, so amperage through 1 is equal to amperage through 2 is equal to amperage through 3. The amps going through this circuit are the same everywhere. So if I put an ammeter right here versus right here, they would read the same. Okay, if we're looking at something that's in parallel, that's not the same case. So we need total resistance. We got 3 plus 6 plus 2, so that's going to give me 11 ohms total. Okay, why do I need the total resistance? Because I need to figure out the amperage going through the circuit. Okay, or I need that for the voltages, I suppose, also. But if I have this 3 ohm resistor and that has 6 volts going through, I can calculate the amperage here, which would also be the same here, which would also be the same here. Okay, but I need this total resistance in order to calculate the amps in the circuit. So let's go ahead and use Ohm's law. Total volts, we got 6 volts. Okay, so Ohm's law, V equals IR. So my 6 volts is equal to the amps, which we're trying to find, times our resistance, which is 11 ohms. Okay, so divide both sides by 11 ohms. 6 over 11, we get, 0.5454, so it's 54 repeating. So our amperage is, let's say, 0.55. 0.55 amps. That's the same everywhere. So that's going to allow us to calculate the voltage in each one of these three now. So 0.55 amps for this one, 0.55 amps for this one, 0.55 amps for this one. So now we can either use our picture or we can just use Ohm's law right here. Okay, so it's again V equals IR, so it's going to be amps times resistance. We just multiply those together, so 0.55, and you might want to use the 0.5454 to get the best answer. Okay, so that's what I'm going to do. So I'll take that times 3, and I get 1.6363, so let's say 64 volts. That's a repeating decimal again. And then here we're going to take 6 times that. I got another repeating decimal, so 3.272, so 3.272 and then I'm probably going to get a repeating decimal there again, 1.09. Okay, and now if I wanted to double check things, if I added these three voltages together, those should equal, it's 6 volts or very close. So if we do 1.09 plus 3.27 plus 1.64, we get 6.0009, which is about 6 volts. Okay, so that's just a way to make sure that you did this correctly, but you also have to understand series versus parallel. This is a series circuit, or everything we calculated here is in series, and sometimes they're a combination of series and parallel, like we have down here. Okay, so we're going to try this one next. This one is from Positive Physics. Okay, so we're going to be working through this, and then you should have enough practice to continue working to finish those. Okay, so I want you guys to pause the video and see if you can work through this on your own, and then start the video back up once everybody has a answer written down, and we'll see if you are right. Okay, so in our circuit here, let's get rid of some of this stuff. Let me get rid of this so I can have more room to work. I have 240 volts going through my circuit. I have a 300 ohm resistor there, a 100 ohm, a 200 ohm, a 200 ohm. Okay, so let's fill out our table. 300 ohms for A, B is 100 ohms, C is 200 ohms, and D is 200 ohms. Okay, voltage, our source voltage, 240 volts. Power will get there, amps will get there. Okay, so if we start to kind of, let's see if we can use a highlighter here. We start to follow the way our electricity goes. We go here, and we have an option to go in that one. We have an option to go in that one, and we have an option to go in that one. So these three are in parallel. Okay, and you can obviously see that there are 3 lines in parallel. However, once we're on this one, okay, these two are in series. So that means that those two are going to add together differently than some of the other things. Okay, so I can put the resistance of this wire together as one. So that, or I guess not the wire, the resistors. This would have 300 ohms of resistance going through here. Okay, so I'm going to treat this like 3 separate wires in parallel. So remember how to calculate the total resistance in parallel. It is 1 divided by 1 over resistor A plus 1 over resistor B, which we're going to call this right now because we have this wire, plus 1 over resistor D there. Okay, and we put that in our calculator, and that is a 3. I know it kind of looks like a 7. So 1 over 300 plus 1 over 300 plus 1 over 200, and divide 1 by that answer. And I get a total resistance of 85.7 ohms. Okay, that's the way that works out in parallel. All right. And so since we have that total resistance, we can start calculating our voltages. Actually, we can start calculating our amperage, because remember, in parallel, the voltage is the same. So voltage of 1 is equal to voltage of 2 is equal to voltage of 3. So the voltage going through this wire is the same as the voltage going through that wire and that wire. So if we have 240 volts pumping through there, then we got 240 volts here. So we have A is getting 240 volts, B and C are getting 240 volts combined, but we have to work with that, so we'll kind of skip over B and C here, and then we'll write 240 volts for there. Okay, So let's start working through this one. So we have 240 volts going through there, 240 volts going through there. And then this one we have 240 volts going through, which this is going to break apart into these two resistors. Okay? So V equals IR. I'm going to take my voltage divided by my resistance here. I'll write that there for you so you can see it again. So divide by resistance and I'll get my amperage. Okay, so 240 divided by 300 and we get 0.8. And that is in a 0.8 amps. And then let's do, so that one's done. Let's do D here. So 240 divided by 200. Oops. And we get 1.2 amps. So that one's done. 1.2 amps. And then we have to do this one. So remember, since there's one path here, the amperage through these two is going to be the same, right? Because we can't, in series, we're kind of thinking about this stuff up here. Series, the amperage was the same. These two resistors right here are in series. So they're going to have exactly the same amperage because there's only one direction for that electricity to go. So let's use this, figure out our amperage, and then we can break that apart to figure out the voltages. Okay, so we'll have 240 volts, and we already did this once, so we get a 0.8. So both of these are going to have 0.8 amps going through them. And now, again, we can use our picture, our diagram, or we can just use our table. It's I times R, so if we multiply those two together, then we'll get what we want. So we have 80 volts going through this one, and we have 160 volts going through that one. These two together should equal 240, because remember we have 240 volts going through this strand here. And our total amperage, so we had 0.8 amps here. We had this one with 0.8 amps, and this one with 1.2 amps. If we wanted to double check our total amperage, we take our total resistance and our total voltage, which is 240, and then we can calculate our total amperage. So it's V equals IR again, so 240 divided by 85.7, 2.8 amps. Okay, and in order to get our amps, we would add the amps from this one, and this one. Those are the three directions, which would be that one. Those two are the same, they're combined, right? And then there's the 1.2. So 1.2 plus 0.8 is 2, plus 8 is 2.8 amps. Okay, so you can see how we calculate that a couple different ways. And then power, we need to figure that out. That's just volts times amps. So take those two times each other, and you get your power. So I have 672.11 watts. And then we just multiply these. 240 times 0.8. That's 192 watts. And then 80 times 0.8. 64 watts. And 160 times 0.8, 128 watts. And then finally 240 times 1.2, we have 288 watts. Okay. And I'm going to check something here just because I'm curious. So let's see if we add all these together, if that gets us our total wattage. We have 288 plus 128 plus 64 plus 192, and that does indeed give us our total wattage. Okay, so you could say another way to check your total power would just be add up all the power from the resistors. Okay, so go ahead, there should be one just like this, so you can refer back to the video if you need to. You need to finish your positive physics stuff, the complete problems 1, 2, and 3 by class, I think Wednesday. Okay, I have one other example down here just to kind of look at it because it looks a little different than some of the other ones. Okay, but when you look at these, you really need to kind of think about the way the electric current is going. So if I follow this wire, oops. So if I follow this wire here and I hit my first resistor, there's really only one direction to go there. Okay, so the wire keeps going, and then down here is where it starts to do some funky stuff. Really, there is only one path for this to go. Okay, when there's only one path for the electric current to go, that means that this is a series circuit. Okay, I would add all my resistances together just like normal, and that would get me my total resistance. Voltages the same way, and then your amps are the same. Okay, so this is actually, it looks kind of ugly, but it's actually a pretty simple circuit. Okay. So hopefully this helped you review a little bit with the solving circuits. If you guys would like to right now, you can take a bit of a break. So give you about a 1 to 3 minute break. Topic of conversation would be where you went for Thanksgiving. Did you go visit family? Did you stay home? Did you do things virtually? And then what else? If you visited with family, if you were staying home, what did you eat? Okay, a couple of conversations that you could have with each other, and then we'll keep rolling. All right, so back at it. We're going to talk about a few circuit components here, and then I have a different video that we're going to switch to, and I'll show you how to do inventory on the Mr. Circuits. Okay, so the most common piece in a circuit is the resistor. They're used all over the place. I showed you guys these in class last time, and there's a specific color code to the resistors. Okay, we have a 4-band, a 5-band, and a 6-band color code. Okay, I think the ones we are going to be working with are either 4 or 5. We won't be working with 6 color bands. And there are color codes that go with those. Now, I don't expect you to memorize them. I have a way for you to do that if you want to. But the first 3, 4, or 5 color bands will tell you how many ohms resistance that resistor is. Okay? The last one, which is usually like a brown or a black or a gold or a silver, is going to tell you what's called tolerance. Okay, so we have these here. So a tolerance is kind of like a percent of error. Okay, but this would be like a percent of amount of electricity that will go through. So this would be plus or minus 5% of that current, plus or minus 1% of that current, plus or minus 2% of that current. Okay, and here are your color codes. So if I'm looking at a resistor, so if I'm looking at this one right here, the first digit, so that would be a red, that's going to be a 2. Second digit, that's a violet, so that would be a 7. And then the third digit is a blue, so 276. And then this one is going to tell me my multiplier. So the first 3, depending on what it is, so you can kind of see on a 4-band, you're going to have the first 2 tell you the numbers, and the third one is your multiplier. And this one, the first 3, it's usually the second to last one, unless you get to the 6th band, is your multiplier. So right here, so 276, and then this is a black. Okay, so that just means it's times 1. So this is just 276 ohms. Okay. If I look at the one up above, okay, so we'll get rid of this, we'll look at one up above. Let's look at this 4-band. So this first one is a red, that means it's a 2. Second one is a green, so that would be a 5. And then this is my multiplier, which is an orange. Okay, so I'm going to go down to my multiplier, that's 1,000. So this would be 25,000 ohms, which is 25 kilo ohms right there. Okay, let's try this one. I know it says the answer right there. Let's give it a shot though. So first one, yellow. Find the yellow, that's a 4. And then I have a blue, so that's a 6. And then I have a black, which is a 0 right up there so you can see it. And then I have an orange again, which is 1,000. So this is 460,000 or 460 kilo ohms. Okay, so I will give this chart to you guys when you need it. We're going to have a quiz over these once we get close to the end of the circuitry unit. Okay, and you'll have this chart and you're just going to label how many ohms a resistor would be, just calculating it using the chart. It's fairly straightforward. Okay, the only thing you might have to know that's a little bit different would be on a 6-band, your second to last color does not tell you the multiplier. That's another tolerance, or that's actually the tolerance, and then the last one is a temperature coefficient, okay, which is basically going to tell you how well it does if it gets hot or cold. Okay, so it's 100 parts per million, 50 parts per million, 15 parts per million, 25 parts per million. This is not that necessary. We're going to be working with usually the 4s and 5s. Okay, so if you would like to memorize that, right there, something you can use to memorize your colors. Big bird runs on your garden, but vegetables grow wonderfully. I don't know how many people actually memorize this, but there are plenty of acronyms out there for you to memorize this. But this would be black, brown, red, orange, yellow, green, blue, violet, gray, and white. Okay. So if we have an orange, brown, gold resistor, what's the resistance? See if you can get it from what I just said here. So big bird runs on. So this is a 0, 1, 2, 3. Right? So orange is a 3. Second orange is a 3. Black, brown, okay, that's a 1. However, this is a 4-band, so that doesn't follow the 1. We can kind of cheat a little bit here. Does anybody remember what the multiplier was for brown? Okay, the multiplier goes 1, 10, 100. So this would be 1, 10. So brown is times 10. So this would be 33. Not times 1, it's times 10. So that is a 330 ohm resistor. Okay, let's check it out. So we got orange, orange, and then brown. Right, so that's 330. And then if you really wanted to be a rock star, gold is our tolerance. So your tolerance would be plus or minus 5%. Which the tolerance doesn't mean a whole lot to us right now. We're looking for mostly the resistance there. If you want something to be more precise, then obviously you want something with a smaller tolerance. Okay. So here are some more resistors. So we have our typical resistors right there, which you guys saw pictures of. This is the power resistor, or also it's called a heat sink, or a heating element, I suppose, either one. And then this guy right here is a 10 tera ohm resistor, so it's quite a bit larger, it's different materials. And then this is our symbol for resistors. Okay, if we wanted to, maybe we can try to get this one. So that's a red, orange, black, brown. So red, orange, black, brown. Do you remember the color codes? So it's Big Bird runs on, so Big Bird runs, so that's a 0, 1, 2, and that's a 3, and then we have a black brown, so Big Bird, so that is actually, this is the, since it's a 4, that's our multiplier, so it goes 110, so this would be times 10, so 230 ohms. That's a 230 ohm resistor right here. Okay, and you guys will be pretty much just matching colors up with resistors unless I give you the chart. Okay, so another piece is a capacitor. We talked about this already. This is what they look like, and there is going to be a number on there, and they will also have labeled how many farads there are. Okay, so that is measured in, that's the capacitance. Okay, so capacitor has capacitance. It has two terminals, and a lot of the time you're going to be paying attention to these because one's going to be positive and one's going to be negative. One is longer than the other unless they're damaged. Okay, so they're measured in farads. A lot of the time they are in microfarads. A 1 farad capacitor is pretty massive. Okay, so they're going to be nano, micro, and millifarads, but most of the time they measure in microfarads. Okay, and we talked about this a little bit in class the last time. Okay, so this is the electric symbol for a capacitor, and remember when I explained this, these have a specific amount of, let's use a different color here, electrons that are allowed on these plates. So once they build up enough electrons, one of them will hop over, and then that's how we continue the flow of electricity here. It builds up on this plate. When there's enough, one bounces over, and then it keeps moving down the line. Okay, but they work as a battery. If I got rid of this battery in this circuit here, my capacitor would have some sort of power left over to charge up or to light up a light until it discharges. Okay, and here's a good analogy for you. So capacitor is like a water tower. The water isn't used from the tower unless excess stores are needed. So in Seward we have our several water towers. Those don't get touched until we actually need them. Okay, capacitors work the same way. Capacitors don't drain their power until the circuit needs it. Okay, and here are a few more pictures of capacitors. There are these smaller ceramic ones like this. Well, we're going to be working with both of them. Okay. And this is the example of a camera that I gave you earlier. Okay, so if you want to take a second to read this here, this is another use for a capacitor. Okay, so they're using touchscreen phones all over the place. And one other piece we're going to talk about here before I actually have you guys get the circuit kits out would be a diode. Okay. A diode is a one-way valve for electricity. It only allows electricity to go one way. It does not go backwards. Okay, so this one, we got our one-way going right there. Okay, it has a low resistance because it's just like a wire, but it doesn't allow electricity to go the opposite direction. Okay, so those are kind of important. Those would be like a backflow preventer, I guess, if you think about water or something like that, but they can also be used as an on-off switch. Okay, or a fuse of sorts, so that way you don't have electricity going and blowing up your electronics. Okay, I don't have these notes in Google Classroom if you wanted to look at it. Okay, and I mentioned this already the other day as well. Okay, so on to the parts inventory sheet, and this will be a separate video, so you can go to the next video and I will show people how to inventory their sheets. Please have everybody at each, or have each table get a Mr. Circuit Lab, and we're just going to work on inventorying today just so people can kind of look at the things and see what they are, and then after we're done with the inventory you will have time to work on your positive physics stuff. Okay, so please switch to the next video. We'll talk up through the inventory and go from there.